All right, hello everyone. My name's Taylor. I am from the Pico CTF team here at Carnegie Mellon, and today I'm going to do the second video in a two-video series about C programming and then buffer overflows. So in the first video, I talked mainly about C syntax and how the C language looks. We wrote two C programs together, and it was kind of an intro to pointers and that sort of thing. So this video is going to be a little bit more in depth than that. It's going to be about actually what buffer overflows are and how to get into binary exploitation. But to fill in some of the gaps, because it would take a while for us to cover all of the content you need to be able to truly understand buffer overflows quite in depth, you can come over to PicoCTF, log in, and then hit this playlist button in the top right. And the first playlist here, low-level binary intro, will give you most of the content that you need to be able to build your knowledge and understand buffer overflows. So what I'm going to go over is mainly under this binary exploitation category. Um, and I'm going to go a little bit more in depth into like what the stack is, etc. But if you can solve these challenges like debugger, learning about a debugger is very helpful, learning about assembly is very helpful, and then command line, ASCII encoding, all this stuff is all stuff that you need to know to be able to do buffer overflows, and it covers the minute details that maybe we are not going to get to in these videos. But I really recommend doing this and solving the challenges. Like each puzzle piece is a challenge um, meant to, you know, have you practice some skill, and yeah, that'll prepare you well to actually get into this video about binary exploitation. Um, yeah, so back to the slideshow. Okay, so like I said, last week I went over reading and writing C, and we wrote two programs. So I'm going to assume that you know how to read and write basic C, and if we see functions that are kind of more complicated, I'll talk about what those mean and how to read them and understand what they're doing. So what do we need to do to be able to do a buffer overflow? So the first thing we need to know is information about this data structure called a stack, and then how a stack is used when we run programs. We need to understand what machine instructions are and how they're used in programming. We need to understand that there are certain functions in C that are unsafe because they don't do bounds checking. And then we need to be able to use certain tools to be able to read programs and then exploit the vulnerability in the program and get the flag, or in the real world, discover a vulnerability that can be used in some sort of attack. So that's what we need to know. We're going to kind of go over these piece by piece. So the first thing is, what is a stack? So a data structure is just a more abstract, well, they're called abstract data structures, but it's this concept that we use for different um, operations on data or storing data. So a stack you can think of as last in. So the last in piece of data is the first out. The way I like to think of it is like a stack of plates. We can't take from the middle or from the bottom without lifting it up, or lifting the plates on top of it up or something. Um, but we can put on the top and take off the top. And so that's what a stack is. It's just um, a data structure, kind of like a stack of plates, that you can only put data on the top. So you can push something onto the top or pop it off the top. And we can't do anything to the middle or to the bottom. It always has to be on the top. And there's a few advantages to this. I'm not going to dive deep, but the main advantage is that it's fast and it doesn't take up a lot of space. So that's the stack. Like I said, there's these two operations, push and pop. But before I go into that, data structures can store any type of data. So from integers and primitive types to strings and objects and whatever. And so the stack does just that. It's just a data structure. So like I said, you can push an item to the top of the stack, or you can pop an item off the top of the stack. So we start with an empty stack, so there's nothing in there. And then we push two items on in these two instructions. So we push a 1, then we push a 2, and then we push a 3. And now in this one right here, it says 3, 2, 1. The only operation we can do, we can't touch 1 or 2. The only thing we can do is pop 3 off or push something else on. So what we do is we pop 3 off. So there's the two operations you can do um, on a stack, on a basic stack. So that's all fine and dandy, but how does that actually get used during the execution of a program? So we use a stack while we're running programs to store local variables, parameters, and return addresses. So in this example program that I've put here, it actually starts on line 12 when we run the program. So we create an integer variable, we take the user input using scanf, and then we call a different function even or odd. And so when we call this function even or odd, what we do is we put its parameters on the stack. We put the return address of main that when even or odd is finished, that it's going to jump back to. And then we have space on top of that for the local variables that even or odd is going to use during its execution. So to illustrate that, I have this diagram here of the stack. So when we're executing main, on the bottom we have the parameters for main, which in this case we don't have any. And then we have the return address that once main is done executing, the program is going to jump to. And then we have the local variables it's working with. So in this case, it's probably just input. And then we have the top of the stack. Then when we call this even or odd function, we put more stuff on top of the stack. So we have main stack frame, but then when we call this new function on line 20, we push its parameters onto the stack. Then we push the return address on the stack. And then we have space for its local variables as well. So, oh, excuse me. When we do this, or when we execute the even or odd function, and it's done printing, whether, of course, the number is even or odd, it uses this return address to jump back to line 20 where it was executing and keep going in main. So that's where those return addresses point. And this is how a stack is used in a program. We're constantly logging because a computer doesn't know anything that you don't tell it. So we're constantly logging the information that we need on the stack and in registers to be able to find what we're looking for and what we need to operate with when we call different methods. So one tool that we use to do that is the stack. Okay, so we have in computer science, we have two different types. Well, we have a lot of different types, but we have two main types of architectures. So we have 32-bit architectures and 64-bit architectures. Most of us are probably using 64-bit architectures now because that's what most, if not all, modern CPUs are engineered for. But there's also CPUs that have 32-bit architectures. And most of the introductory to buffer overflow challenges that you'll be solving use 32-bit architectures. And there's different conventions for each architecture. So for instance, on the right, we have the 32-bit architecture stack layout. So we have the function parameters on bottom, then the return address, and then EBP is a register, which we'll talk about later. So we also store EBP, we store exception handler related info, and then we store local variables and callee saved registers. But on the 64-bit stack, we store a little bit more stuff. So we have local variables, we have allocated space if used, stack parameters, then homing space, homing space, homing space, homing space, and then the return address. So the stack frame in 64-bit compared to 32-bit looks a little bit different. So it's useful to know. If you want to check on your computer what architecture you're using, I think you can do about my PC and then see. Okay, it actually doesn't tell me. Huh. Let's see. We can just Google this. I want to tell what architecture your computer is. Okay. It's in a system. Information or system summary, maybe? Oh, x64 based PC. Perfect. So x86-64 is a 64-bit architecture. And so you can just go to system information and look at the system type, and it'll tell you what architecture your PC is. Most likely, if you're using Intel-based processors, it'll be x64. If you're using ARM-based processors, it'll be something different, but still 64-bit, most likely. Anyways, back to the slideshow. So the stack frame looks different for different architectures. And like I said, a lot of the introductory buffer overflow programs on picoctf are in 32-bit architecture. And we'll go over how to install and run the different software packages in Linux that it takes to be able to actually run these 32-bit programs. Because if you just have a 64-bit operating system, you won't be able to run these 32-bit programs unless you take some extra steps. So we'll go over that as well. Okay, so what are registers? So underneath C, when C is compiled, so it's taken from source code, which looks like this, and then it's translated into this language called assembly, and then um, that assembly can actually run on a computer because it's in machine code. And assembly makes use of these things called registers. So this is the 32-bit register convention here. Some of them have specific purposes, but some of them are just general purpose for storing data. And before we got to 64-bit architecture, we used 32-bit architecture. Before we got to 32-bit architecture, we had 16-bit architecture. And then before we had 16, we had 8, etc. So um, because of that, we have different names for different registers. So in 64-bit architecture, this EAX register is changed to RAX. And then half of the RAX is EAX, which is 32 bits. Then half of EAX is AX, which is the 16-bit version of EAX. And then there's AH and AL, which are both 8 bits. So different registers have different names, and it can depend on what architecture you're working with, what things are going to be called. So this can get quite confusing if you've never looked at assembly language before, um, but it's useful to know about because when we start trying to solve buffer overflows and we start looking at the addresses of where things are, we're most likely going to be at least looking at some assembly, but not really having to understand terribly much, but just understanding what we're looking at. So registers sit right on the CPU. They're the fastest form of memory, um, and we have a limited amount of them. So this doesn't list all of them, but you can see that, we only have like 1, 2, 3, 4, 5, 6, 7, 8 registers, which makes sense. So, and then 64-bit, I think we have 16 registers. So things change and we only have a limited amount of registers. So we have to optimize our programs to use closer memory first and then farther away memory later. But we're getting into some details that don't really matter. Just know that registers, some of them have specific purposes and some are general purpose, and they're the fastest form of memory, and assembly language makes use of them. So one thing that's important to point out is ESP and EBP are both used for the stack. So if we go back here, you can see that in 32-bit assembly, each function has a base pointer, which points to the base address in the stack of a function's frame. So, and we have to store the base pointer as well, so we can restore it after we call a different function. So the frame pointer, or the base pointer rather, is related to the stack. And then RSP always points to the top of the stack, or ESP rather. RSP is the 64-bit version. So ESP always points to the top of the stack. And so we're going to use it in our debugger to be able to find where we need to go to look at the stack and examine what's going on. So ESP is, if you take anything from this slide, ESP points to the top of the stack, and that's it. So, okay, where do return address point to? So when a program is being ran, the CPU has to know what to do. So it needs a list of instructions. And those instructions are stored in memory at certain addresses. And the instructions, we call them machine instructions, and they're just encoded ones and zeros that mean something to the processor. So we kind of tricked the CPU into thinking that they do something, which they do. They mean something, but that's how the CPU knows what to actually do to actually run a program. And so this is the output of obj dump, which dumps the memory addresses, the byte codes, and the assembly translation of those byte codes to your terminal. So you can see this file is called auto-generated, and the memory address of what we're looking at is right here. So this first line here, move gs 0x30 cx. So this is assembly language right here on the right. And then this is the byte codes that are encoded to mean this. And then this is the address that this code lives at. So I'm going to repeat that because it's kind of complicated. So this tool called obj dump dumps out the assembly, the byte codes, and the memory addresses of an executable. And so on the right here, we have the assembly language. So move q gs colon 0x30, so hex 30 cx is the assembly. And then these are the byte codes that are encoded to mean this string of assembly. And then this is the memory address, which this code lives at. So this is code that runs on your machine to make it do something. And it has to live in memory, so it has an address. And at the very lowest form, code is just ones and zeros. It's just numbers that we've encoded to mean different things. And so this block of assembly can be encoded to look something like this online, like a function or a C source code. So every time you compile your C code, it gets translated into something that looks like this and put in memory. And the return addresses, oh my goodness, excuse me, the return addresses on the stack are pointing to one of these addresses where the code lives, where it needs to return to. So see this return instruction down here at hex 10023FF. This is a return instruction. So once this executes, the CPU is going to look to the stack, so wherever this return address is, and then it's going to start executing code where the stack is pointing. So say that the stack was pointing down here to hex 1002409, then this return would jump here and we would start executing code. And we keep doing that until we get to the end of the program. Okay. Wow, I had a whole diagram I wasn't looking at. So this return address, like I said, points to somewhere in the code where we're going to jump to once we finish the function, and we're going to continue executing code. So the next question is, how do we attack this? So what if we could change the return address in a function to be able to jump to some malicious code that we've put into memory ourselves? That's an option. Or what if we injected our own malicious code onto the stack and then changed the return address pointer to jump to the top of the stack or wherever this code is stored and start executing the code that we put on the stack? You'd think that we would write programs or write programming languages or design our systems such that we couldn't do this. And there are protections in place now in modern times, but this is the most basic form of binary exploitation, is injecting code onto the stack and then changing the return address to the address at the top of the stack, or not the top, but wherever that you injected the code. And then, doing whatever you want. You can execute whatever code you want because you have control over what you inject. So this is the most basic form of buffer overflow. And another thing is that we need to know is the C functions. So, we have to be able somehow to overwrite what's on the stack or write out of bounds, for instance. So what we could do is we could take advantage of these unsafe functions in C that take user input, and we could write out of bounds, or we could write too much data to something. And then because our local variables are stored on the top of the stack, if we wrote too much, we could overwrite all the space, and the return address and the parameters and the local variables or whatever because there's no bounds checking. And so lots of C was written using these unsafe functions. And because we can overwrite them, and because we're writing to a certain amount of space called a buffer, they're called buffer overflows. So now let's look at what it actually looks like given an overview. So typical tools that we use to do buffer overflows, GDB, objdump, Python, with specifically the library pwn tools will be helpful. And we're going to get into some examples. So, okay, firstly, the first one I want to do is buffer overflow 0. And so I've already downloaded the code on my WSL instance, which looks kind of ugly. Let's see if we can change. Oof, that's even worse. Red. That's even worse. Not black. Okay, whatever. So I've already downloaded the files here, so I'll do an ls and you can see, oh, that looks much better. Okay, we have vuln and vuln.c, which they give to us in this challenge. So it says, let's start off simple. Can you overflow the correct buffer? The program is available here. You can view the source here. So I clicked these two links and it downloaded these two files, vuln and vuln.c. So this vuln is the compiled version of this source code. So additional details will be available after launching your challenge instance. So let's go ahead and launch our instance and see what it gives us. Okay, so it wants us to connect to this vulnerable program using netcat. And then it gives us this IP address and this port number to be able to connect to. So let's go ahead and see what this is all about. So if we pull up my WSL instance here, I'm going to copy this, which I apparently didn't do, and then paste too many times, and then do that. Okay, so it looks for input. We're going to say something. The program will exit now. Can we do anything else? No. Okay. So it looks like we're able to give this program input, and then it's going to exit. But we know that somewhere there's a buffer overflow vulnerability because, of course, we're trying to solve a CTF challenge. So how would I go about solving this? So the first thing I would do is I would look at the source code in VS Code. We can see a few things. So the first thing, I always start at the main function, and then I follow the trajectory from there because that's where a C program is always likely going to start. I see we're opening a flag file. I see that we're printing out if there's not a flag file to make one, then we're getting the flag. We're setting up a signal handler. Okay, so this is interesting. So I want to say of interest. So what we're doing is we're setting up a signal handler to handle this sig-seg v signal, which if we look up what sig-seg v signal is, segmentation violation. So a segmentation fault. So when a programmer code tries to access an invalid memory location. Okay, so that tells me that we're going to be doing something with return addresses and trying to get the program to jump to something that's invalid. Okay, and so then when we go back to the source code, we see that the sig-seg-v handler function is what's going to be handling it. And if you want to check out the signal function, what we can do is we can go onto WSL. So if I go to PowerShell, WSL, hopefully this boots up quickly. While it does that, okay, there we go. So I can do man3, I can type, and then signal. No manual entry for signal, man signal. There we go. Okay. This gives us an overview of signals and like what each signal means. We can send signals, and these are different signal types, but this function, what it does is that whenever this signal is sent, it calls this function to handle it, and then we return if this function is called, So if we receive the signal, then this function is called. So if we try and access a part of memory that is invalid, then this function is called. So we do some stuff here that doesn't look particularly interesting, but then that we can see that we're taking user input like before. So we have printf input, and then we declare a buffer, we gets the buffer, and then we gets is in the function, and then we call this vuln function. So they pop up to vuln, we have another buffer, a size 16, and then we stir copy the input into that buffer, and then we printf, the program will exit now. So all we're doing is giving input, and it's getting copied into two different buffers. So yeah, and then let's inspect this sigsegv handler. Okay, so if we receive a segmentation fault signal, then we're going to call this function, which it looks like is going to print out this flag variable that is read in from this file. So how we're going to get the flag? We are going to have the program access some sort of memory that doesn't exist. Simple enough, right? Because we know from the slideshow that we can overwrite this return address if we have an unsafe C function. So let's go back and see what's unsafe. Okay, gets unsafe, stir copy, unsafe. So we can put however much input we want into this first buffer, call this function, and then it copies and using stir copy into this buffer, which is also unsafe. So to overwrite the second buffer, all we really need is 16 or 17 characters, and then that should theoretically solve our problem. So, okay, that's how I interpret the code, or I mean, what the code says. Code leaves a little room for interpretation. But if we go back to here and we go to buffer overflow 0 and we launch our instance again. Sorry, there was a bit of time between the last one because my computer stopped working because the CPU got too hot. So it's been a journey, but I'm going to restart the instance and we can download the source code, but now we also have this netcat thing here. So I'm going to go to PowerShell, hit Q to exit my manual, clear this off. Then I'm going to go ahead and connect to this program. Okay. So we have our input. So let's put 17 things in here. So 5, 10, 15, 17. Let's see if this works. It might not. I don't actually know. Do that. Program works now. Okay, so that wasn't enough. We didn't overwrite enough. So let's just, say who cares. Send a bunch. Oh, perfect. There's the flag. Okay. So what have we done? First of all, don't copy this flag and enter it in your own thing. That would be cheating. We know when you cheat, by the way. Anyways, going back to the video. So we got the flag because we gave all this input, and from the source code, we know that we're using vulnerable functions, gets and stir copy, and we can overwrite the stack. So what we did was we went back here and we overwrote our local variables and got into the return address and made the program try and return to some area in memory which doesn't exist. And then because it tried to do that, this signal segmentation fault got sent, and then this function handled it, which printed out the flag. Okay, so what if we wanted to test locally? Well, to do that, let's go here. Let's say ls clear. I'm not in the right directory. We have 0. Okay, so now we have, oh, don't pay attention to that. Okay, so now we have these two functions and we can run vuln. We can actually use the file command to figure out what it is. So it's an elf file, which means it's supposed to be run on Linux. It's 32-bit. It's in Little Endian, which Little Endian is actually a pretty important concept. So if we Google Little Endian, we can go to Wikipedia and we can see that, where is what I'm looking for? Considerations, byte addressing. That's probably where it is. Okay, so most computers, or not most, but some computers are in Little Endian, which has a significance increasing from left to right, which means that when you're looking at memory addresses, they're going to be backwards when you're looking in memory. So whenever you're looking in memory, remember that numbers are backwards. if the file is little endian. If it's big endian, it looks normal, but if it's little endian, then it kind of flips it. But anyways, we know that it's least significant bit, which means little endian, executable, processor it can run on, dynamically linked. So we can get a bunch of information from this file command. Side note here, most computers in modern times, like I said before, are 64-bit computers. So to be able to run 32-bit programs on 64-bit computers on Linux, you have to install certain libraries. And I think I can figure out, no, it did not. Hopefully you didn't hear all those those bells that window just sent at me for not being able to find what I was looking for. But you can actually, and so running 32-bit programs on 64-bit, not Windows 10, I want to do Linux. So you have to install certain libraries. This is the link that helped me. So you have to add an architecture and then install these libraries to be able to actually run 32-bit programs on a 64-bit Ubuntu distro. Um, anyways, so if you're getting like, something that looks like bash can't, or like bash, this file does not exist, like an error that looks like this, then it just means that your system can't actually run the file. But anyways, so we can get a lot of information from that file command, and we can also do local testing. So we can run it. So /vuln, if I could type. So please create a flag.txt, which we know that this is the case because we can see that if we don't have this file in our directory, it's going to ask us to create it. So let's go back here. We can use the touch command flag.txt. So that creates a file. So now we have the file here. And then I'm going to actually put something, well, I'll just do echo, this is something, and then I'm going to direct that into flag.txt. So now we'll cat it out and our output is now in there. So now if we want to find our solution locally, we can just run the program because we have that flag.txt file. This is right in as our flag, and then we successfully solve it, and then we get out the flag that we created locally. So you can do this local debugging, and you'll really want to do this when you get into more complicated buffer overflow challenges. Okay, so that's the first buffer overflow. What about the second one? So to do the second one, let's actually read our instructions here. So let's go, we're going to do buffer overflow 1. So it says control the return address. Okay, that's a pretty big hint already. So, oops. If we go into our slideshow, we can see that when we overflow it, maybe we could be clever and we could put our own return address in there. And so it could jump to some sort of malicious code or, some sort of code that will let us find the flag. So let's go back to our picoctf thing and read the rest. So additional details will be available after launching instance. Okay, so let's go ahead and launch the instance and give it a second. It's probably going to give us a netcat link. Yeah, so it gives us the netcat link and then it gives us the compiled program and then the source code. So I've already downloaded those on my machine and put them in this bf1 directory. I'm going to remove dumped and flag. And so these are the two files that they give us. Let's do this. So once again, I'm going to run the file command to figure out what I'm working with. So I have a Linux executable, 32-bit, little endian, dynamically linked. Okay. So it's the same one as the first problem. So I'll be able to work with it on my machine here. And then I want to look at the source code. So let's go into here and actually open up our buffer overflow 1 source code and see what's happening. So I'm going to start with the main function set vbuff. Don't really care about that. GIDT, GID. This doesn't look super interesting. Okay, here we go. Puts. Please enter your string. And then we call this function called vuln. Vuln defines a buffer called buff, uses gets on the buff, and it says, okay, time to return, fingers crossed, jumping to, and then this function get return address, which must be imported somewhere because I don't actually see it in the source code. Okay, so first thing to identify right off the bat is this unsafe function gets, and this buffer is size buff size, so the buffer is 32. So we're going to be able to put 32 characters in this buffer. And what else? Okay, unsafe. We call this vuln function. So when we overflow this buffer, we're going to be actually inside of the vuln function. So it would probably be worth inspecting what the stack looks like when we call this vuln function so that we know how many characters to overflow this buffer with, um, so that we can control the return address. Okay, how are we going to do that? Well, luckily there's this tool called GDB, and it's GNU Debugger, and what it'll let you do is it'll let you execute a program and stop in the middle so that you can inspect different things, about memory or what's happening in your program. And so the main use case for this is obviously writing software. If you have bugs in your code when you're writing software and you want to debug it and figure out what's happening, you use GDB to make your code better or to make it work. But we can also, debug programs that work so we can inspect the memory and attack them. And that's what we're going to do with this particular program. So to get started, we can do GDB vuln, which is the name of the program. And then, like I said, we want to inspect the stack during the execution of this function vuln. So what I'm going to do is set a breakpoint, which will pause the program, at vuln. So B stands for breakpoint, and then the function is called vuln. Hit enter. And so now we have a breakpoint at this memory address. Okay, so now I want to run the program and inspect the memory. So I'm going to use this command called run, which is going to actually run the program. It says, please enter your string, whatever. But now we are in this function vuln. And then to figure out where we are, we can use this command disas, disassemble, and then the function that we want to disassemble. And these little arrows show us where we are. So right now, we're executing this memory address, 804.9289. And yeah, so we're in this vuln function. How are we going to inspect the stack? Well, I told you about these registers back in the slideshow. So ESP is always pointing at the top of the stack. So if we want to inspect the stack, we can find out where the stack is based on the value stored in ESP. And so we need to print out where what our registers are. So we can do info registers, or if we wanted to shorten that, we can just do IR and it'll print out the same thing. So EAX, ECX, EDX, blah, blah, we don't care. Then finally we get to ESP, which has our stack address. So we don't actually have to copy and paste this. What we can do is we can just use $ESP, not RSP, and it will give us, the address. So how do we print stuff out? So I'm throwing a lot of GDB commands at you, which you may not be familiar with, which is totally acceptable and normal if you're still learning. So there is this thing called the GDB cheat sheet that I like to use that contains, lots of useful things about GDB that you can refer to when you're doing this sort of debugging work, trying to figure out, just exactly how many characters to write and what address to write, etc. So yeah, you can refer to this GDB cheat sheet if anything I'm saying is overwhelming or if you feel like you're not going to be able to remember these, debugger commands. But so we want to print stuff out. So if we go to our cheat sheet and the variables and memory thing, we have this command called x /, and then we can tell it how many units, what format, and what unit. So I want to print, oops, in my thing, I'm going to use this x command. I want to print 20 units. I want them to be printed out in hexadecimal. So x, which we can see down here, print as hexadecimal. And then I want to do words. So in 32-bit architecture, we're working with 32-bit, data size. That's how big our data is, each piece of data. And so there's 8 bits in a byte. So 32 divided by 8 is 4. So each piece of data that we have is 4 bytes. And a word is a short way of saying a piece of data that's 4 bytes. So I want to print them out as words to get accurate measurements since we're working in a 32-bit system. So I'm going to do X, W, and then I want to print out what's at ESP. So I'm going to use $ESP. Okay, Perfect. So we can see this is what's stored on the stack. So it starts at 0x, so hex 804C000. Then we have some more data here, and we keep going, going, going. So what looks like a return address to you or to me, this 804 stuff? Because if we, well, actually, we haven't done it yet, but just from my experience, I know this looks like a return address. So to prove it to you, I can use this tool called objdump. And so objdump, what it does is if we do a help, it displays information from object files. And so what we want to do is disassemble the file so that we can see all the memory addresses and how they correspond to different functions in the program. So we're going to use objdump to disassemble it. So we'll say objdump, use that disassemble option, and then vuln. And then I want to grep for, well, actually, that's not grep. Let's just do it. Okay. So we have memory address, bytecodes, and then the assembly that they correspond to, and then the function that we're in right here. It's like memory address, bytecodes, assembly. Okay. So if we go back to our slideshow, you'll remember that I showed you something similar. Memory address, bytecodes, and then the assembly instruction that they actually correspond to. Okay, so if we go back here, we can see that 804 blah, blah, blah looks like the memory that our program is in. So if we go back to our stack, so let's execute the function or the program again. We'll set a breakpoint at the vuln function. We'll run it, check out our registers. Everything looks good. And then we will print out the memory at RSP. So 8, I want to do words and then ESP. So 804C00, that looks like a return address. 804.932F, that looks like a return address. Do you have any more in here? We don't. Okay. So what is the stack going to look like after I actually, when I'm actually going to input the buffer? So we can go back to the source code and we can say, okay, gets. Well, I'm actually going to be putting my input in on this function called gets. So we can inspect the stack literally right before this instruction. So we'll go back to GDB and we'll disassemble our vuln function to see where we are and here. So we can see that that function gets is called down all the way down at this instruction. So we got like 1, 2, 3, 4, 5, 6 different instructions before we actually call this gets function, which our stack could change, depending. We're editing ESP here, so the stack is definitely going to change as we move down these instructions. So let's do this. We can use this command ni, which stands for next instruction, to continuously move down until we're right before the gets function. So I'm going to do it 5 times. So I hit enter once. Whoops, could I please hit enter? There we go. So 1, 2, 3, 4. And I want to check to make sure I don't go too far. Okay, I haven't gone, so I'm going to do next instruction one more time. Okay, disassemble vuln again. So now we're here. And now I'm going to do next instruction one more time. And we are looking at the stack literally, we will have the stack literally right before we call this gets function, which will be taking our input. So then we can print out memory again. If I go up here, ESP, and see what we're dealing with. Okay, so we have some more stuff at the top of the stack. Looks like another return address. Here's the return address we saw before. And yeah, so if we wanted to overwrite the return address, we'd probably have to overwrite this specifically. But how do we know what address we should overwrite it with? Well, if we go back to our source code, we can see this when function, right? So we have a buffer called flag, or sorry, called buff of flag size, which is 64. We open a file called flag.txt. If that file is not in our directory, then we're asked to create it. Or if it is, then it reads the file and it just prints out the flag. So it looks like we need to return to this when function. And how do we know what address our when function is at? Well, if we get out of GDB and we use our tool obj dump and disassemble again, and then our function, and then we grep, which means search for the word when, there's our function address. So now we can start sending input to the function and trying to refine our payload so that we overwrite the correct return address, depending on which one it is. You can see there's 1, 2, 3, 4 return addresses, 5, 6 return addresses here. So you need to figure out which return address we need to overwrite, how to actually overwrite the buffer, how many characters to overwrite before we start editing the return address. And you can use these tools to do it, GDB, objdump, and looking at the source code through some sort of text editor. So I'll leave the program for you to solve the rest of it yourself. I believe there is a solution. Yeah, there's a solution right here. So if you get stuck, feel free to come to this solution, but I really recommend, the reason I'm not walking through it with you is because I want you to do it yourself, and you'll learn the best by doing it yourself. So you can refer to all the concepts we went over here, like what we're overwriting, how the stack looks, um, more in depth if you Google things. And yeah, you can start feeding this program input and hopefully cleverly overriding the return address to be point to this when function and get the flag. So, yeah, that's really all I had for this video. I hope you learned something, or at least learned a little bit about buffer overflows. I will say there are some good resources to learn more. So we have this playlist on PicoCTF. We have this learn page where you can go Pico primer, and then you can come all the way down here to a little about the C language and binary exploitation, and that'll kind of walk you through some of the things that we talked about. There's also something about assembly and registers. Hopefully this video at least kind of told you why those things are important for binary exploitation. And then there's also other resources. So there's this thing called Pwn College, which is out of Arizona State, which is very good for, learning buffer overflows and binary exploitation. And it's free to sign up and has a lot of resources getting started. And then, you know, lots of cool stuff, software exploitation, system security, program security, intro to cyber, very cool stuff revolving around pwning, which is, software security. And then there's also a bunch of other resources. So if I just look up, how to do a buffer overflow, OWASP, Stack Overflow, Medium, Geeks for Geeks, InfoSec. There's a lot of different resources that talk about binary exploitation, buffer overflows, and then you can kind of continue down that path of knowledge to get into more advanced stuff like ROPing, etc. So yeah, I hope you learned a lot, and um, we hope you play PicoCTF and solve some buffer overflow challenges. And more big picture wise, we hope you stick with cybersecurity and choose it as a career. Anyways, thanks for watching, um, and I'll talk to you later. Bye.